In the next few lectures, including the present one, we shall calculate and plot the shear force and bending moment diagrams for various loads acting individually on a beam of cantilever type. This lecture shall focus on a point load P acting on the tip of a cantilever beam of length L. Let's have a cantilever beam AB with the left end A fixed and right end B free. Let's show a point load P acting downwards at its tip. Before finding the resistive forces and moments at various sections along the beam length, it is in general necessary to consider the beam in static equilibrium so that the unknown support reaction forces and reaction moment can be found out. These reaction forces and moment once found out shall hence be used to find the resistive axial force, shear force and bending moment at various sections of the beam, provided the fixed support becomes the reference end, from where the distance of the section, that is variable x, is measured. But for the cantilever beam as a special case, we may proceed directly with the estimation of the unknown resistive forces and moment at the section without the need of finding the support reaction forces and moment, only if we consider the free end as the reference end of the beam for the measurement of the variable x. This is because the right part created by virtue of the section only needs to be balanced and analyzed as a free body, with the left part including the support reaction forces and moment discarded. Hence, for cantilever beam, we can minimize our effort by avoiding the calculations for the support reactions and moment entirely. One can wish to use either way, that is, considering end A as reference, requiring calculations of support reactions before finding the resistive unknowns at the section, or considering end B as reference and finding the resistive unknowns at the section directly without the need to calculate the support reactions. Here, let us consider the free end B as the reference end from where the distance x of the imaginary section is measured. We shall hence write equations for the unknown resistive shear forces and resistive moment developed at the section, considering the right part as a free body in static equilibrium. Remember that there shall be no actual force developed at the section, as there is no horizontal force acting on the beam. Let's show the projections of the ends of the cantilever beam downwards. So, we may draw the datum lines denoting the zero values for both the shear force and bending moment diagrams and name them accordingly. The shear force acting on an imaginary section at distance x from the reference can be written in the form of an equation. We write shear force at x equal to plus p, since the shear force tends to balance the free body vertically and is assigned a positive value as both the forces create a clockwise couple as per our sign convention adopted. This equation is found to be independent of the distance x, hence the same value is expected at all the locations along the beam length. The shear force diagram hence has a plot represented by a horizontal straight line denoting a constant value of plus p. It is a good practice to always denote the range of x for which a particular equation is written beside it. Here, the shear force at x equation is applied for the value of x greater than and including 0 and less than and including the length L. The bending moment acting on an imaginary section at a distance x from the reference, written as m at x or bm at x, equals minus p times the distance x, minus being the sign adopted representing hogging bending moment. The bending moment at x hence is a linear function of x, meaning that the power of x in the equation is exactly 1, for which the plot of bending moment diagram shows an inclined straight line. The bending equation used applies to the complete length of the beam in this case as well. That is, bending moment at x is valid for x values greater than or equal to 0 and less than or equal to length L. Note that the bending moment is maximum for the maximum possible value of x, that is, when x equals L. In this case, mx equals minus p times L. For the sake of completeness, we name the locus obtained for shear force at x as constant and for bending moment at x as a linear curve. In the next lecture, we shall find the shear force and bending moment for the case of uniformly distributed load acting over the entire length of a cantilever beam.